So, questions? What are people doing? We're sort of in like the middle of groups, right? And it can get a little technical for sure. And I think the plan is this week we'll try to finish this chapter on groups and talk a little bit about vector spaces. Talk about matrices, but we want to kind of consider linear algebra when we get there a little more generally than maybe you would experience in a matrix algebra course. But we'll get there next week, I think. So this week we want to finish up groups, and or at least what we're going to look at with groups. It's a big subject. Still, people study these things, so we're just scratching the surface here. So I want to start off with a theorem, and then we'll get to some. This is a theorem that's we should have really covered last week, but didn't have quite enough time. So, and it gives us a sort of characterization of normal groups. Normal groups are, well, maybe I'll just give away the punchline, the normal groups. So the reason they're important is because, well, we've talked about how we can partition a group into left cosets. Yes, we talked about that last week. Now, when we do that, we define this set, which is the set of left cosets, G over H, where H is the subgroup. So we talked about things that look like G over H. This is just a set of left cosets. And we have to be really sensitive to the words we're using. So here it's the set of left cosets. Collection of things. Subsets of G. If H is normal, only if H is normal, will the group structure, the law of composition for G, induce a group structure for this quotient? If H is a normal subgroup, what we'll see in a couple of lectures, or maybe next time, is that this set inherits a law of composition from G, and in fact is a group itself. So we can talk about the quotient group of G by H. So this proposition is just a proposition that gets us a little bit closer to that construction. So we want to prove it. Okay, so let's talk about the proof. Now, I didn't define right cosets. I think I mentioned them briefly and just said they're the same idea as the left coset, you know. So there's not much more to say about it, but we'll get to part 4. So if we're going to do one of these proofs of the following are equivalent, then the way you prove it is you're going to show that one implies, I mean, you can show it in any order you want, as long as you make a full cycle, but the most typical thing is to say that 1 implies 2, 2 implies 3, 3 implies 4, and then 4 implies 1. You can show all those implications, then you've shown that they're all logically equivalent statements. The first statement is the definition of normal subgroup. So this is the definition. This is the definition here. And then the second is really just kind of a silly restatement of the first, right? Well, maybe you need to show the other way, but okay. So, so 1 implies 2. Let's do that first. So by 1, G, H, G inverse is certainly contained in H. Right. But in fact, you can think of this as a map, right? So you can think of this as a map. But we consider conjugation. It's a map. say H, G, H. This is H going to H. Now then there's an inverse map, right? There's an inverse map. Conjugating by G inverse gives an inverse. And what this means is, so the point is that this gives you the other inclusion. So i.e., so because you have an inverse, you can say, well, if H is an H, then so is G inverse HG. This is conjugation by G inverse. It's by 1. By 1. So G inverse this is it. GH. So we're saying that, so thus H is contained. So there you go. So we started out with the obvious implication here, and we wanted the other implication. And we just said, okay, well, so this is the idea as you can construct an inverse, but then if be more specific, if we have any element in H, this element is also in H, and then if I conjugate this element by G, I get something in the conjugate of H, but that is exactly H. That's in. So get this conclusion. It's sort of a little bit of a questions? All right, so for 2, so someone can help me with 2 implies 3. But, yeah, multiplied by G on the right. So we have GHG inverse equals H. This implies by multiplying, GH equals G. And you can, this is fine. It's okay to do this because even though this is a set of elements, you can multiply the entire set and you'll get this. You can use associativity as well. Okay, 3 implies 4. Well, that's nothing. There's nothing to say here. I will rarely write this word, but I'm going to write it here. Okay. Certainly, if the left coset is equal to the right coset, then it will be equal to some right coset. This is identifying which right coset it is. I mean, 3 is more specific than 4. And the last one, 4 implies 3, is 4 implies 1. So what do we have to do for that? Let me do this instead. Let me actually say the following. Okay, good.
Like if by multiplying together, so every left coset is a right coset. So if we multiply by G on the left, that means we have a left and a right coset. We can multiply by G inverse on the right. And that's that statement up there. That's
So, okay, so if we have G on the left, so let's see I think this will help to clarify what you have to figure out here. So let's assume what we're given, right? We can't assume more. So suppose G is any element in G, then 4 says, then there says the following thing, sorry. Then there exists, I'll call it G tilde, G, such that GH equals H G tilde. That's what 4 says. They're not necessarily the same element. It says that a right coset is equal to some left, a left coset is equal to some right coset. I can't multiply this on the right and say, okay, I mean, I think if I conclude 2, I mean, 2 is, this is sort of, actually, I want to just say this is an if and only if proof here. Like if certainly if you have GHG inverse is equal to H, then 1 is also true. That's not, I'm not gonna, so I'm gonna actually just show 2 here, make it easier on myself. So let's say we have GH is equal to HG inverse. What can we say? We can do what you suggested and multiply on the right, say by G tilde inverse. Let's do that. Okay. But G tilde is not G. Yeah. Can anyone tell me an element in H? Give me an example of an element. Subgroup. The identity. The identity is an element in every subgroup. So there is some H with GH, G tilde inverse equaling the identity. If I multiply that equation on the left by G inverse, well, I guess it doesn't matter to me. If I multiply this equation on the right, say by G tilde, I'll get this equation. G tilde is equal to GH. Right? Multiplying on the right of both sides by G tilde. But what is then the inverse of G tilde then? I mean, I guess I could have figured this out without this. Like, okay, this is clear. What is G tilde inverse? H inverse. How can I expand that? H inverse G inverse. Okay. So H is equal to GH G tilde inverse equals GH H inverse G inverse. But now this associativity still holds. And when we look at this, this is the right coset of H multiplying by an element of H. But that's just H. And that follows from the fact that this is a partition. The right cosets form a partition. That makes sense to anybody? Say anybody? Does that make sense to anybody? No, doesn't make sense. So hold on a second. I'm going to make this claim. G H G inverse. And I'm going to say because H inverse is equal to H. Why is it true? H inverse is a right coset of H. Right cosets partition G. identity is in both sides, right? Right, because H times H inverse, this is equal to identity. That's in here, and identity is in here. So both of these are right cosets. This is if you want 1 times H, right? And they have an a non-empty intersection, so they're the same. It's a partition. Okay. So that's why I'm able to make this replacement right here.
Could you also argue that big H inverse equals H because H is a group and is closed in the composition?
Yes,
H
you
inverse
could
is
argue
not
that.
an H?
Yes, there's other ways of it. Multiplication. So one of the things you should think about when you have a group is if you multiply the whole group, or like think of multiplication by some element as a map of the group, it will permute everything in that group. It will permute all of the other elements around because it's a bijection. Right? So by multiplying by H inverse, big H, it's just moving everything in H around, but the set is the same. You don't leave the set. Okay, so this proves this, and it will come up later when we want to show that multiplication for normal in the quotient groups for normal subgroups, that this is well defined. We won't use this proposition. Now we're going to get something more concrete. So if that level of abstraction was way too early in the morning for you, that's okay. Let's get to something which I think for many of you is more familiar. Talk a little bit more about congruence. Modulo n. And so last time we finished the lecture just introducing the idea, because we were really talking about left cosets of n times z, which is a subgroup of z. And here, I'm going to use, I'll put plus here. Additive, this is the additive group. And we gave a couple of examples, but the idea was, I'm sorry, not n times z. This is an additive group, so I have to use the operation I'm dealing with. So cosets, you want to use whatever operation. So we're using multiplicative notation a lot because that's the operation, but C plus has a special addition that is also not. All right, so what are these? So n plus z, well, we can just write it out. This is the set of integers that look like this, n plus a, where a is an element c. But this is, as I said last time, this is all integers. Pardon me. It's too early for me. The cosets of nz. Nz is the subgroup. I want a plus nz. My goodness. Sorry, guys. I'm screwing your notes up here. Sorry, guys. This is all b plus n. Sorry, guys. All right. All integers with remainder a after being divided. Sorry for that. My head's on straight. So this is the idea of a left coset of nz, of our subgroup nz. Nz is the subgroup. So we looked at an example like the 3. You can look at any examples you want. I don't know, maybe it's helpful. I don't know. Should we look at another example to remind ourselves everyone's happy? Okay. So it turns out, so by hand, what we can do is we can define this quotient group in this case. So, and maybe before we define the quotient group, let's see what this is as a set, but let's make the proposition. This is in Arden. I'll just write it out. So there are n congruence classes, mod n. So mod n, that is the equivalence relation giving us this partition. Or to be a congruence class is to be one of these left cosets. Namely 0, 1 to n minus 1. And so here a bar, this is the shorthand notation for a plus n. Equivalent. I think I got this notation. Equivalence class. This is not so. So the proof of this. Well, maybe I'll say one other thing. So thus, index. This is some vocabulary we had last time of and z and z. Sorry, z. Pardon me. Is this index would be written. I'm going to drop the pluses. I think that they drop them. You know that we're talking about addition. Confusing me. That's a number of the cardinality of the quotient set or the set of cosets, the left cosets. The left cosets here, of course, is the same as right cosets because we're dealing in groups. So there's no issue here. Now, as I said, one of the things that's really useful for normal subgroups is to be able to find a group on this quotient, a group structure on the quotient, or sort of inherit one. And this is even better. In fact, we can, these things, a set, which is denoted Z mod n, these things form what are known as a ring. We'll get to that in more detail, more gruesome detail much later. But we can define all of the arithmetic we want with this. Maybe not all of it, but some of the arithmetic. We can add them and we can multiply. And so that's the next thing we want to do. So let's define addition one way. I'll actually define both addition, multiplication. Follows. If I have two classes, A and B, I can add them. Following way, I have two classes, A and B, and I multiply them, I'll take the product. And what's the problem, guys? Aside from my inability to like make here, what's the problem with this definition? A priori. You know, like, if I just showed this guy on the street, probably say, I said, no, really, you want to pay attention. Then what would they say? What's the problem? So let's take an example. N equals 2. What are the congruence classes of n equaling 2? Congruence classes mean equivalence class or left cosets. Yeah. 0 and 1. Good. By this theorem. But what if you tell an elementary school kid the congruence class 0 mod 2? They're going to say, what are you talking about congruence class? I've never heard of that. And then they're going to call their parents. So if you wanted to have that conversation with that kid about congruence class mod 2, what would you call 0?
Even numbers?
The even numbers. Even numbers. And the congruence class 1 is the odd numbers, right? So you've got 2 of them. Now, you said 0 and 1, but I say even and odd. Is there another element that will give me 0? Another way I could write 0? I choose another even number, 10. 2. I can choose any even number I want, and it's that equivalence class. So here I'm saying, okay, well, I can choose a number here, and it could be any even number, and it's going to be any odd number. And then I could choose a different number and different even number. And how do I know I get the same thing over here? So in other words, you're making a choice when you represent one of these. When you represent evens as 0, you're making that choice. I could have chosen it to be, 2,000. I could have chosen a different number, and that would still be the same set. So how do I know that if those different choices aren't affecting the class I'll get on this other side? And so this is what we need to verify, that they don't affect them. But this is a lemma. The lemma will hopefully make more precise what I'm saying exactly. So if A is congruent to A prime, mod n, this is this equivalence class or equivalence relation giving us this congruence class. And B prime is congruent to B mod n. Then their sums are congruent. This means that I can choose any number I want from a given congruence class, add it to any other number I want. And when I take their sum, I'll get something that's going to be congruent to any other thing that I would have gotten from different choices. And the products are also congruent. This is what we're trying to prove, is that what we just did is what's called well-defined. We want to show that addition here is well-defined, that it did not depend on the choices I made when I wrote A and B. Does it make sense? Seeing a few nodding heads, but there are a few like that furrowed brows. Thumbs up, great. I feel like I'm on Zoom even though I'm in person. What do they call them again? That's notification. Okay, questions. Be bold if you have a question. Okay. So you may say, well, I know an even plus an even is an even, and an even plus an odd is an odd, and an odd plus an odd is an even. So why do I, what is all this about? You know that. Well, what about Z mod, 2 billion? Like, do you know that if you chose different classes there and you added them up, that you would get the same thing? It would be independent of the choices you make. Maybe you do, and that's okay. But here we want to show that that's true. Okay, yeah. Yeah, go ahead.
This one right here, are you saying that those two sets added together equal sets added together?
So it's actually true that that these two sets, when I add them together, I will get this set. So if I add sets up, and then it is actually true that I will get the thing on the right. And in the case of integers, it's also true that I can multiply here the sets. There's a notion of the product of sets, and it will work. It does not work in more general contexts to multiply and have equality. It does in this case. And that's just a feature because multiplication doesn't have inverses. However, in this case, you have some uniqueness. so it somehow works there. But I want to kind of use an element-based approach to say, rather than thinking of these things as sets, which is the proper way of thinking of them, rather than thinking of them that way, let's think of the elements. And in some sense, let's think of the choices we make when we write a coset as a bar, or when I write evens, as 100 bar. I'm choosing 100. So when you make that choice, we want to understand that things are independent of that choice. I guess that's the best way. But indeed, you can add, and in this case, multiply these sets. So first, before I prove it, let me just say what this means, because I'm not sure I'm using notation I'm not sure I defined last time. So we say that A prime is congruent to A, or maybe I'll just write X because I'm going to use A or B here. Mod N, if, only if, when I take their difference, this is divisible by N. So that's just the definition, and it's equivalent to the notion that they give you the same. This is also if and only if X plus NZ is equal to X prime plus NZ. So they're the same left coset. And so the proof of the claim, let's call this 1 and let's call this 2. So for 1, you just say, okay, well, take A prime plus B prime minus A plus B. This is equal to A prime minus A, B prime minus B, but N divides both. So N divides, oops, divides the sum. When I say both, I mean both A prime minus A and B prime minus B. And for 2, it's a little bit, I don't know, it's a little bit more pain in the. So consider A prime B prime minus AB. Well, I want to say, this is okay. Before I consider this, let me move down. So suppose, since A's, so suppose A prime minus A is equal to N times Q, N times P, and B prime minus B equal to N times Q. Then this is equal to A prime times B plus NQ minus B, AB, which equals N times A prime Q plus A prime B minus AB, which equals N times A prime Q plus, and now I can factor out a B, A prime minus A B. But now both, this is divisible by N, this is divisible by N. So we're done. Because I didn't need the A prime one. All right, so that's a proof. Now, what is the consequence of this? What is the consequence that we can do arithmetic mod N? well, like, 100 different quiz questions on my math problems. I don't know. Like, there's a lot of silly like consequences that you can write, which are sort of surprising. I think. So sort of surprising things you can say. So what's an example? Fun arithmetic. Scare your neighbors. In more ways than one. So you could just like go around and say like 3 to the 1,000 has remainder divided by 5. Right? You see that? Yeah. So how do you see it? How do you do it?
I mean, the way that I see it is you would take 1,000 mod 5, and that would just be 0.
Okay. So I think you're doing something that might be a little questionable. The arithmetic that you have, well, it's okay. It's the first, I mean, everyone should do some questionable things at some point. Mathematics. Okay. So now what we have here is we have these two operations that we can do mod at. However, we do not have this operation. We can't do this. We cannot exponentiate. So for example, why wouldn't this work? So let's see. Yeah, I think I've got to think about it. What's a good counting example? This one low number because the high number is going to be. Yeah, that'll work. Okay, so if I take, let's just say we take 5, n equaling 5, and we can take 2 to the 6th. I think this will work. What is 2 to the 6th? 64, really? Okay, good. I mean, I could figure it out if I given enough time. So what is now this mod 5 is what? Is 4. However, in this case, 2 to the 6th, this is 6 is mod 1, so this is 2 to the 1 is 2 mod 5. And we know because of that earlier proposition that 2 is not equal to 4. And this will fail like a lot more, but I was trying to find a low number example. I think it works for 2, not 2. So when you exponentiate, you really are just taking that thing to that many times that power. You can't mess around with the exponent so much. But that would be really nice if we could. So what's another thing we'll maybe leave that here. So what's another argument for this guy here? Yeah.
I think you would just have to find 3 to some power that is like can be multiplied to get to 1,000. So it's in like number terms, basically.
No, you're right. Let's look at some powers of 3, right? So there aren't that many. We know when we're looking mod 5, we only have 0, 1, 2, 3, and 4. There are 5 of them, but we only go up that high. So if we start with 3 mod 5, we can square it. What do we get? 9, which is 4, but okay, let's think of it as 9. Let's square 9. What do we get? 81. What's 81 mod 5? 1. Now 1 is a great number. 1 I can square and I get 1. 1 I can cube, I can get 1. I can take 1 to any power I want and I'll get 1, right? So what we can say here is we can say 3 squared is 9, 3 squared squared is 1. So that's 3 to the 4th is 1. So Artin says this in the book, and I'm going to do it, which is I don't like writing congruent mod blah over and over and over again. I just say we're talking mod 5. So I'm just going to write equal, and I'm going to lose the bars. Yes.
So are we just saying that the integer 81 mod, and then that equal sign now means mod 5?
So say again, if we're sort of
So
saying,
like, are we just, is the thing on the left just the integer 81, or is it?
it's just, I'm just saying,
Right.
no, it's, I'm thinking, okay, what is this? What does this equation mean? What it means is it means that if I look at this class 81 mod 5, this is equal as a set, as a left coset to 1. It's like what I was saying earlier with, evens. You can choose different numbers as representatives. But as a set, as a coset, they're the same. Just choosing different elements in that coset. So that when I write it this way, I'm saying this is saying 81 plus 5z is equal to 1 plus 5z. These are the same sets. I'm able to add and manipulate these sets like they were numbers. So now I've got 3 to the 4th is equal to 1. But now that means that we know 1 to anything is 1. It's 3 to 1,000. So you don't want to take 3 to the 1,000. That'll take way too long. I don't know. Please don't do that. So there's this is like a baby version of the following result about Euler's totient function, which I'm just going to mention. I'm way behind on my lectures. It's also called the phi function. Phi tells you the number. If I put an n, it tells you the number of integers between 1 and n relatively prime to n. So for example, we could say phi of 2, this is just 1, because 1's the only thing relatively. Phi of 3 equals 2. Phi of 4 also equals 2. 1 and 3 are relatively prime. Phi of 5 will equal 4.
So could you just define prime numbers as like any number for which phi of n equals n minus 1?
Yep, you can do that. Weird definition. It's possible. Now, these integers between 1 and n that are relatively prime are precisely those to n are precisely those integers that have a multiplicative inverse mod n. I'll write it. I'll do better. The integers between 1 and n that are relatively prime n are precisely those integers with multiplicative unit or multiplicative inverse. So Z mod n has two operations. It has addition and it has multiplication. That's what we showed up above. We can multiply these classes and we can add them. And it's, well, these are well-defined operations. Z mod n is a group under addition. You can add them, they're additive inverses, you just take the negative, it's fine. Z mod n is not a group under multiplication because 0 is there. 0 always presents a problem. But other things are there that present the problem too. So if I was thinking Z mod 6, 2 is there. How do I get a multiplicative inverse of 2 mod 6? I need something to multiply 2 by to get 1 mod 6. But I'm not going to be able to do that. Why won't I be able to do that? Why not? 1/2? Well, I don't know if I would. Like for example, in Z mod 3, 2 squared is 1. 2 squared is 4, which is congruent to 1. Z mod 3, 1 and 2 form a group. Z mod 6, 2 is no good. Yeah, it does, but it's too confusing. So let's say we multiply by, okay, so let's say we had one. So suppose otherwise, suppose 2 times A is equal to 1. So we had that mod 6. Well, then what happens when we multiply this mod 6? Then what happens when we multiply this by 3? 3 is equal to 3 times 2A plus 6 times A. Wait a minute. What is 6 times A? 0. 3 is 0 mod 6. That's saying 3 equals 0, but we know this is false. We have the full list. When we're below that number and above 0, 0, 1, 2, 3, 4, 5, those are the unique, those are all the classes we have, and they're different. I'm saying they're equal. They're not. No inverse for 2. So, however, if I take 5, 5 is relatively prime to 6, right? I square it. What's that congruent to? 1, right? Divide by 6, I get a remainder 1. Apply all the relatively prime ones. Those are all the units. They call them units. So the multiplicative have multiplicative inverses, and they form a group. So if m is any integer, oops, GCD, relatively prime to n, then m to the phi of n is congruent to 1. Right? Why is it true? I will release you. This isn't about algebra. I'm really sorry. I'm really slow. I might have to adjust some homework this week because I'm sure I'm going to get through it. Why is this true? This is a bit of an application of group theory.
I don't have anything to look at. People, I mean, M and M are co-prime.
Yes.
So if we said,
So as I said, so let me call this set up here. Call this set equal to Z mod n times. It's a group. It's a group. It's the group of guys with a multiplicative inverse. Z mod n times m is in Z mod n. Relatively prime. So it's congruent, whatever it's representative less than, it will be relatively prime. What's the order of this group? We just said what it is. E of n. We can look at the cyclic subgroup generated by m. What's the order of this? Nobody knows. However, what do we know by Lagrange? Lagrange told us something about the order. It has to divide the order of the larger group that it's in. So that means that if I look at the number, the order of m, that's going to be 1 for the order. K is the order of m. Sorry, I'm almost done. Then this will be true. But since K divides phi of n, we get you can divide an integer here. We get 1. So for example, I mean, if you look at something like, I don't know, 23, and you take it to the 4th power, it has remainder 1 when divided by 12. So you can like start getting, you know, a bunch of nice numerical results like right away from some of these basic group theory results. Okay, guys.